Thank you very much for the introduction, for organizing the seminar, and for having me. I'm really happy to be here, and I'm looking forward to this seminar in general. So today I will tell you a little bit about topological data analysis and my recent research of topological data analysis in machine learning. And this is mainly in collaboration with Jan Zuckerberg, who is here. Okay, so let's get started. A few words about topological data analysis. So the general idea is that in topological data analysis, we want to use topology to understand the shape of data and encode it with features. And we would like this characterization to be informative of the data. So we would like to explain these features we have. And then, of course, we have to efficiently compute such features, otherwise they will not be useful for data analysis. And then another property that we work a lot with is stability. So this relates to robustness to noise. But why do we use topology? I mean, why do we go back to this field of pure math? So in general, I would like to argue that topology is good for describing shape characteristics of data because it tells us about connectivity relations on a data set. And then for those of you who study graphs, so machine learning on graphs, topology can be seen as one step forward after network theory. And then we will see how we use topology to find subgroups, clusters, cycles, which are things that usually matter in data analysis. Okay, so let's start with the topological data analysis pipeline. The idea here is that we start with a point cloud, but we also see that the input could be different. Actually, we can take as input very many things. And then we construct a geometric object representing this discrete data set. Then we build homology out of it and transform this geometric information into sequences of vector spaces and linear maps. This is a way to simplify and encode the geometry of these geometric objects. And finally, we have to find descriptors for these sequences of vector spaces and the linear maps. So let's say that the first part from Viatoris Rips to the vector spaces is quite standard in TDA. If this was a TDA audience, I would not go through this, but I think it's interesting to understand what are these features and what they tell us about this data. So I will take 5 minutes to explain this first part. And then my research is really like how to describe this homology representation of the data, which are good descriptors for machine learning and what do they tell us about the data. So that is more the research part. So let's start. We have a discrete data set and we want to find its shape. So we want to approximate it with a geometric object. The way we do that is by considering epsilon balls around these points and constructing a graph. So the graph we build is a graph where vertices are our data points, and then there is an edge between two vertices if these balls, these spheres overlap. So it tells us about proximity relations. And these are balls of radius epsilon. Then once we have a graph, we want to take this geometric generalization of a graph that is called simplicial complex. And the way we do that is to build a geometric object built of simpler ones, which are vertices, edges, triangles, tetrahedra, geometric blocks built all together. And this is by looking at the cliques in the graphs. So if we have a clique with 3 vertices, all-to-all connected nodes, this will become a triangle in my geometric representation. So this is a way to go from the discrete data set to a geometric object. And these are actually where we can study the topology. The topology is of geometric objects, of topological objects. Now, one thing to say is that we have chosen this radius epsilon of the ball, but often it's not clear which is the right epsilon to choose. So this threshold should actually vary. And if we vary this threshold from a very, very small epsilon to bigger and bigger, we see that these geometric objects become more and more connected and more higher dimensional. The idea of persistent homology, which is this main tool in topological data analysis, is to look at features across this filtration of geometric objects. So we want to have a multi-scale approach on the data. We want to look at geometric features along different scales. And let's say that still comparing these geometric objects is quite complicated, because on the computer you can encode simplicial complexes, but they're not very easy to deal with, and it's not the best object, and it's not our final one. So we will do one more step, at least.
Just a question, yes. Martina. So yeah. when you construct the balls,
yes.
Is the choice of metric, is that important?
Yes, yeah, a great question. So that's the most important thing. So all depends on the metric you take on the data. This is really proximity relation with respect to a metric. And this is really the key, like finding the right metric to compare data points and seeing with respect to a metric, what is the geometric information with respect to another metric, which is the geometric information, and comparing them. And this is a key point. Feel free to interrupt when you have questions. Okay, so we have these geometric objects that are built from these proximity relations, and we want to simplify them, extracting homological features. So what is this homology? We want to take vector spaces that tells us about connected components and cycles. So when I say H0, this will be connected component. If I have a torus here, this has one connected component, so its H0 will be K, because K is the field. It's a vector space of dimension 1, because we have one connected component. When I say H1, this will be cycles. In a torus, you can see that there are two cycles which are independent according to an appropriate notion. One is this cycle here, and the other one is this cycle here. So we look for classes of cycles. I will not explain the details, but this is usually taught in an algebraic topology class or a topology book. So here we have two representatives of H1, and H2 looks at voids. So this is space, and which is enclosed by two-dimensional simplices, by surfaces. This is the type of features that we extract from these simplicial complexes. Okay, so we have this filtration of simplicial complexes, and we compute these homologies. So we get a sequence of vector spaces and linear maps. The maps are given by the inclusion of these simplicial complexes, one in the other, once you enlarge this radius of the balls. And there is a nice theorem in algebra that tells us that since we are considering a totally ordered set, so our set is the real line, the parameterization is on the real line, such sequences of vector spaces and linear maps can be written as sum of simpler sequences of vector spaces and linear maps, and they are called bars. So here we can see the H0, and each bar corresponds to a homology generator, so a feature in our data set, a homology feature in our data set. Here you can see H0, there are a lot of bars because there are a lot of connected components, but then when we go through the filtration, some connected components join and bars will end at this point. In the end, we end up with just one connected component. Here we are looking for cycles and how they persist in this sequence of vector spaces. Here it's the H2. At some point we build a cavity and then it gets filled up. So this is persistence barcode that people in TDA work a lot with. And there is software to compute it. Actually, there is this Ripster software that works very well for the type of construction I have explained, but there's also the Goody library that is being developed by INRIA and also on Python. There's quite a lot of software because these methods are actually used in applications these days quite a lot. Okay, but I produced a barcode as feature of my data set. This is a set of bars or a multi-set of bars if we take bars with multiplicity. It's not quite easy to compare set of bars and how to use them in machine learning. That's not an ideal input. So then comes the other step, that is vectorizations and ways to compare these barcodes and how to introduce them in machine learning pipelines. Here just an example before I show the torus, and we can see a sampling of the torus and how the barcode plots represent these homology features I had explained before. We can see that we have one connected component, two long bars for these two loops, and then one void inside the torus. And sometimes people don't work with barcode, but with this 2D representation of the barcode that is called the persistence diagram. Each bar is mapped to a point on the plane with birth, death coordinates of the bar. So sometimes people work with persistence diagram instead of the barcode plot. Okay, so I mentioned we want to compare such objects if we want to do data analysis. For example, I have a bunch of point clouds I want to compare. I cannot just stare at these barcodes. Also, like averages on barcodes are not defined. There exists not a unique mean. There are a lot of problems in these spaces of barcodes. But at least one can compute some metrics, as for example, this bottleneck and Wasserstein. There's a question? Okay.
It's an AI assistant, you can ignore it.
Okay. Okay. So we have bottleneck distance and Wasserstein distance. They are computing starting from idea of optimal transport distances, and the idea is to match points of two different diagrams. So here we have the blue diagram and the red diagram, and we want to match them. So we find a matching between the points of the diagram, and let's say, what if they don't have the same number of points? We don't care, we can send points to the diagonal, which we consider to have infinite multiplicity. And given a matching, we can compute the cost as the maximum distance in L infinity norm, for example, on the plane of matching 2 points of these two diagrams. And then we take the infimum along all matchings. This is the bottleneck implemented in Goody and used in TDA. And then one can have a Wasserstein version of this, where we don't take the supremum of the distances between the points, but the p-norms of all the matched points, the error of all the matched points. So these are combinatorial distances on the persistence diagrams that can be used to compare them. There are some algorithms that compute them in a decent time, so they can actually be used in applications. What I've been working a lot, but I will explain very briefly, is how to create other distances to compare these sequences of vector spaces and linear maps. And this is a very abstract definition of distance, which is algebraic. And it extends to the more general case where the parameter space is not the real line, but one can have different partially ordered sets. So generalizations of this persistence pipeline. The idea is to declare what is small. For example, I declare bars of length epsilon at most to be epsilon small. And then to say that two barcodes, they are close if they are maps to another one, so these maps between the algebraic objects with which errors whose p-norm is smaller than epsilon. So we prove that if these collections of small objects satisfy some axioms, then actually you obtain a distance, a pseudometric in this way. So this is a very, very abstract axiomatic framework, very, very general, which allows you to define a variety of different distances. one way to define such distances is through contours. We can see contours as ways of reparameterizing the real line in a way which is non-linear, of course. So let's take an action of 0 infinity as opposite on the monoid 0 infinity. This action, if you have A and you want to move by 0, you have to stay on A. If you want to move first by epsilon, then by tau, it must be the same as epsilon plus tau, and then it's order preserving. If you have some extra assumption, you also get regular contours. Now, are there families of such reparameterization? This was investigated by Wojtek Hachulski and Henry Riihimäki some years ago. Well, they found out that every measurable function defines a contour. So there are very many contours, at least as many as all measurable functions. And this action, this reparameterization of the real line, can be defined as how much you have to move on the real line to span an area of epsilon under the curve of your function. So I start with a measurable function f, and I say that I act on A by epsilon. That is how much I have to move to span an area of epsilon under the curve. Okay, in this way, what one can do, one can directly define distances, or a bit more hands-on way to deal with this is to redefine what is the length of a bar. I say that the length of a bar in my barcode is not actually death minus birth, but it is how much I have to move with my contour to go from the beginning to the end, from the birth to the end. So this is how I define the length of a bar. And so you see that if I have bars in this part of the parameter space, their length is this area. And if I have a bar in this part of the parameter space, the length is this other area. So it's a way to scale the length of bars according to where you are on the parameter space in a hands-on definition. With this notion of length of a bar, which is a bit more generalized, one can define a norm on barcodes. What is the norm of a barcode? It's the p-norm of this generalized length. We can call them lifespans of the bars. So I have my barcode decomposition of the module, and I take the p-norm of all the length of the bars, or the maximum if p equals to infinity. So this was introduced by Turner and Scrub as a norm, but recently we managed to prove that this actually follows these axioms that we would like to have, so it defines an algebraic distance. And moreover, for some choices of the parameters, so if we take this function f to be the constant function with value 1, for p equal infinity, we obtain that combinatorial bottleneck I mentioned before. And for finite p, we obtain the Wasserstein. So this is a way of generalizing those two combinatorial distances between barcodes. Okay, so we have metrics, and we are interested in the fact that they are parametrized, at least by this value p of the p-norm and these contours. But maybe one doesn't want just to compute distances between barcodes. One wants to compute features out of them. And one way is through this stable rank. So the way we use metrics is as follows. We choose a numerical descriptor of persistence module, for example, the number of bars, and then we minimize it in metric neighborhoods. So this produces a function which is decreasing, because we take bigger and bigger neighborhoods, and it depends on the distance which you have to compare these persistence modules. It's all about comparing with distances, this business. You have to understand how to compare points in the beginning of your data set, then how to compare these barcodes. It's all a business about metric comparison, I would say. And once we have this stable rank, which is a function, we can compute a kernel. This was Jan's contribution, actually. And so we consider them in a Hilbert space and build the kernel as the integral of the scalar product of two stable ranks. This is useful because it allows us to use kernel methods with the stable rank, so with topological features. And of course, if you want to use this, you have to be able to compute it. And while in general, it's a nightmare for more general posets to compute these stable ranks. It's very complicated mathematically. If you have the barcode and these contour type distances, it's actually pretty straightforward. So this stable rank is a count of the length of the bars or the lifespans of the bars. The stable rank at step t is the number of bars whose lifespan is greater than t. So it's it's a bar count according to the length. But let's see these stable ranks in action on a simple data set. So this is a very simple data set. I will use several data sets, but they are mainly to explore the properties of the methods. We are not really focusing on the data analysis, but more using the data to explain the methods. So here we have 4 different figures, and we sample 100 points from each of these 4 figures with some Gaussian noise around the points, and we obtain point clouds of points on the plane, and they are labeled by the shapes. If I compute H0, so I look at connected component, stable ranks, with this standard action that is just constant. This is how the stable ranks look like. And if I perform support vector machine, I obtain 35% accuracy, which is not good. I'm not claiming it's good, but this is how to see how the stable ranks look like. And if I look at H1, these are the averages, and this is the standard deviation. Then one can obtain 88.5% accuracy with support vector machine classification. And one can play a little bit with these densities and the contours. What we did here was to look at piecewise constant functions and just do a grid search and find the ones that performs best in cross-validation. In this case, this was the one, and we can improve accuracy. So here the message is that by changing the metric to compare these barcodes, one can obtain better features for the homology. This was just a grid search, and it was quite simple. And also, like you see here, we have these curves and they distinguish, and it's about H1, so it's about cycles. And actually our figures, they all have one big cycle. It's not that, apart from the last one, but the first 3, they have a big cycle. So what the persistent homology is capturing is not only the general shape of the point cloud, but also smaller, finer details like cycles that are formed between groups of points and so on. So we have large scale characteristics, shape characteristics, but also medium and small scale shape characteristics. Okay, one thing that happens with topological descriptors is that usually ambient noise destroys the signal. But now we have functions, so we can subsample points and take averages, and this was quite effective from experimental point of view to denoise the data and actually find them to be distinguishable again. And again, here we can change the level of ambient noise by just adding background noise on the plane. And we can see that with subsampling, we get much better accuracy. So our methods become much more robust to noise. Uniform. It was uniform noise on the square. So here we saw that actually converting these sets of bars into function was very good, because we could actually start using simple statistical tools like subsampling, and we could use the kernel methods. So this was a good idea to go to this type of vectorization, and it has some benefits in simple data analysis tasks. Okay, now I will briefly discuss another data set we have been looking. This is a more interesting data set, and I will describe how we used stable ranks for this data analysis. Here we are looking at trees, and we will focus on trees that are actually neurons or microglia cells in the brain. And there are different ways to get barcodes from data. Before I explained how to go from a point cloud. Now this is a different type of construction. We start from a tree, so a geometric object with a function of it. And then we look at super level sets. So all of the geometric object that has function value greater or equal than a threshold. And by changing this threshold, we see that connected components appear in form of leaves and they connect. So these are bars that appear and then they finish when two branches merge. I will not make this precise, but another construction different from Vietoris ribs allows to go from geometric objects to barcodes by looking at functions on these geometric objects. And in this case, we studied these microglia cells from Sandra Siegert's lab at IST. Here is photos at the microscope of the cells that come from different brain regions in the mouse. So this is a huge, very good data set, 40,000 microglia morphologies. And they were not presented to us as images, but already we had the skeleton of the trees. So there was already some segmentation process before. We used these barcodes to understand the branching patterns of these morphologies. And then we converted them into this persistence diagram and persistence images, which are just Gaussian kernels on the points of the persistence diagrams to smooth this. And one could see that there was some signal at the average level, differentiating microglia from different brain regions, but this data is very noisy and it's very heterogeneous, so this was not enough to actually distinguish the single microglia cells. But with some bootstrapping on these vectorizations, we could actually get a dimensionality reduction which reflected the spatial differences of microglia from different brain regions. Again, here, the goal is to find an appropriate metric between this descriptor which reflects differences in biology, as for example, positioning in the brain. And we are also interested in development and the generation of microglia. So this again is a metric problem, which is an appropriate metric which denoises the data enough, but still has features which are related to the biology. And instead of the persistence images, we could use a stable rank and get a similar differentiation. And we also used the support vector machine to understand which was the effect of this bootstrapping. Are we averaging too much? Are we creating signal that is not there at the single cell level? We could see that actually this bootstrapping was just highlighting some signal that was already in the data. So for us, the support vector machine was a confirmation of the visual understanding of the data through the dimensionality reduction. So here we've been using these stable ranks. We didn't change the contour much, but we're working more on this to understand which are parts of the microglia which are more interesting for differentiation. We use these stable ranks for dimensionality reduction and then for classification. And then finally, I mentioned the Wasserstein distance, algebraic Wasserstein distance. This has more parameters than the contour ones, and it can be more interesting. So can we compute the stable rank with Wasserstein distance? This is another thing that we looked into recently, last year. And we found an algorithm to compute the stable rank for algebraic Wasserstein distances. And we found out actually that the stable ranks go down one step at a time, so they don't jump. Every time the function goes down, it's just by one. And so what is important is where this function decreases, and these points are p-norms of the lifespan of the bars. So in the end, the algorithm is quite simple, but we had to do some, we had to have some understanding of the maps between these vector spaces and linear maps, so of the algebra to do that. Okay, and as interpretation of what this p-Wasserstein metric do, we tried it on another simple example. So we created artificially two classes. One class that distinguished, that was different with respect to the number of short bars in the barcode. So these are distributions of barcode. On one side, the short bars have a different distributions, and here small p was good at distinguishing the classes through stable ranks. And then we had another distinction in two classes where actually the length of the long bar was playing a difference. And here it's p equals infinity that distinguishes the stable ranks best. So this is to say that we have some understanding with these parameters, how they relate, not to the data, but at least to the barcodes. And then from the barcode to the data, that's another step. If we do some optimization and we get small p, then we say, oh, well, it's short bars that are signal in my problem that distinguish classes. If it's a large p, it's the longer bars. And then one sees what that meant on the data, where that came from. Okay, so here, for example, we have a data set that has been used in TDA. And this is 3D reconstructions of brain arteries from 98 individuals, and we set up a classification task. So class A was individuals with age greater than 45, class B, individuals with age smaller than 45. The problem here was to find stable rank representation that would be good for this classification task, as it was early in previous work, this work by Bandich and Koffers, it was reported that actually the barcodes were good at distinguishing these age classes, and short bars also played a role. So we set up a metric learning problem based on distances between stable ranks, and this is the objective function, which is designed to have small intraclass distances and large interclass distances. So we want to minimize this objective function, and this is differentiable in the parameters p and of the contours. In this case, we chose a density which is sum of two Gaussians, so it's a Gaussian mixture. And so we have the parameters of the Gaussians and the p to optimize. So we don't have a throughout analysis of the optimization problem. We don't have a theoretical analysis of the optimization problem, but we could see that most times after a number of iterations, the loss went down, and these parameters were stabilizing. In particular, this parameter p stabilized around 1, which is coherent with respect to what was found in the literature. And the contour stabilized to this shape here, which is also interesting because it tells us about parts of the parameter space where the differences between classes happen. So one can, in principle, go back to the data and look at these distances at this time scale, at these space scales, actually, what are the differences in the trees. And we also observed that it was beneficial to optimize all these parameters together. So we obtained better classification optimizing p and the contour together rather than doing that independently. Okay, so up to now, we've been looking at this problem of finding better descriptors of the barcodes optimizing metrics to have descriptors which are best in supervised learning. Another property of topological descriptors, which I think a lot about, is stability. So this property tells us that if we start with an input which is close in some metric, then the topological descriptors will also be close. This is a Lipschitz condition. Stability is a Lipschitz condition. For example, if we start with these two functions, which are close in L infinity norm, then the persistence diagrams will be closed in bottleneck distance. This is one of the first paper about stability in 2007, and since then people have been really working on the stability results for all the topological descriptors. And for us, one of the motivation actually to do these stable ranks was that they are stable. So whatever metric you have to compare barcodes, then the function going from the barcodes to the stable ranks is one Lipschitz, if you take an appropriate metric to compare the stable ranks. So we have from the data to the barcodes, it's Lipschitz. From the barcodes to stable rank, it's Lipschitz. And also persistence images have some stability result, but with respect to one Wasserstein. So it's not with respect to any distance you would have there. So for stable ranks, we have a bit more stability. But then now the question is, in principle, we think this stability is good for machine learning because it tells us that if you perturb your data a little, then your feature will be similar to the one you have. So it's a sort of robustness to noise. But now something that we have started investigating quite recently, but I'm quite excited about this, so I wanted to share it, is do we get some guarantees in adversarial machine learning by using topological features? So in adversarial machine learning, one considers robustness. And if you take a sample with label C, you say that that sample is epsilon robust. If in a metric neighborhood of X, then the prediction is the same. So all the samples will have the same label C. Okay, so this is a metric property. And there are several papers actually showing that Lipschitz networks have robustness guarantees. Which are provable, and they depend on the Lipschitz constant of the network, the neural network, and the prediction margins. So the goal of this project is to understand if neural networks with a topological layer, topological component, are actually robust with respect to adversarial examples. And if this is not the case, then we want to find some, in general, we want to find some architectures which have these properties. I have not talked about deep learning with TDA, but so this is just a taste of it. Maybe one of the main papers here is Persistent by Matthew Carrier at INRIA. And Persistent is a layer for deep neural networks, which takes a persistence diagram. Now you recognize this as an input. So Persistent is a modification of a deep set neural network, which is appropriate for persistence diagrams. Now you can see that there are different channels. Maybe you can think of this as taking H0, H1, H2, and so on. So these are different topological features. And then more or less how it works is that for each point in the persistence diagram, one constructs a vector with a learnable function, and then you have a operation which is permutation invariant because it's a set. We don't care about the order of the points. Permutation invariance, and then you merge all of these together, and then you can concatenate it with another neural network, for example, fully connected. So Jens started to investigate how Persistent works with respect to robustness. And in particular, we use this data set where we have 5 classes, which are points on the plane representing iteration of a discrete dynamical system following that equations, and the 5 classes represent different choices of the parameter R. So this data set first came out in 2017 in this paper about persistence image, but it's now sort of a benchmark paper in TDA, because you see that these patterns have some homological features. We have cycles coming up in these patterns on the plane. And here are the H0 and H1 persistence diagrams. So from the first investigations, it seems that the classification was sensitive to the addition of one single point in the persistence diagram. So you can find an adversarial example classifying an element of class 1 to an element of class 3, just adding one single point in the persistence diagram, and it can be arbitrarily close to the diagonal. So this means that you have found very many, like 80% of the data points had adversarial examples which were arbitrarily close. So this tells us that if you have a topological feature, so the first part, going from the data to the persistence diagram, which is stable, if you connect it to something that is not probably robust, then it will probably not be robust. But so there is still the hope of concatenating these robust Lipschitz topological features with Lipschitz networks and understanding appropriate local Lipschitz constants so that the whole procedure becomes robust and has some theoretical guarantees on the output. So in summary, I gave a bit of a crash course on TDA, what type of features we get from the data, what are the barcodes we worked with. And I hope I gave a taste about this type of research we are now doing in trying to combine these topological descriptors with machine learning and basic statistical methods. And we are very much interested in finding good optimization techniques to optimize the topological descriptors, so to improve and develop this metric learning framework, for example, and understand how this stability of topological features can impact machine learning. Thank you for your attention.